Okay, awesome. Good to see everyone again.
Yeah, good morning. Well,
yeah, okay.
Yes, please. So, last lecture of Geoff Penington, yes.
Okay, yeah, so it's great to see everyone again. So today's lecture is going to be about a load of developments that happened in 2019 involving things called islands and replica wormholes and so on that let us derive the page curve and various other facts about the black hole information problem just from gravity. But before I want to get onto that, I wanted to briefly talk about something I was rather sloppy about yesterday at the very end of my derivation of Lukovitz-Maldacena. So we had reached the point where we'd shown that Zn, which originally was this partition function of CFT on a replicated manifold that we were then going to compute semi-classically in the bulk, could be written in terms of these objects on the quotiented geometry in the bulk. We'd assumed the bulk had their symmetry. And in particular, we had a term that was just linear in n, and then the Einstein-Hilbert action on this quotiented geometry with metric G1n. And then we had a term that was n-1 times the area of this surface gamma, which was picked out by the saddle point equations near n equals 1 to be an extremal surface. And then we had some extra matter terms. So we had n times the partition function with that metric on the quotiented geometry. And finally, we had a trace of rho little b to the n, where rho little b is the normalized density matrix on the region little b bounded by big B and gamma for the state prepared using the geometry G1n, okay, on this manifold with metric G1n. I'll just put by the Euclidean path integral. Okay, so then we wanted to compute Zn over Z1 to the n, because that was what was going to let us determine the entanglement entropy, and we wanted to compute it near n equals 1. Okay? And I somewhat glibly suggested that because this term and this term have proportional to n, they have a factor of n out the front, that they should cancel between the Zn and the Z1 to the n. Okay? Because this is log Zn, so it's e to this thing, and then that should cancel with Z1 to the n. But of course, in general, that's not true, because these terms depend on n, both through the prefactor and through the metric on the quotiented geometry, okay? So for general values of n, then this will just be some different geometry on the quotiented manifold to the geometry we have at n equals 1, and so, you know, the two contributions won't cancel out when we compute Zn over Z1 to the n. Okay? But fortunately, at n equals 1, or at n very close to 1 to linear order in epsilon, they are going to magically cancel out. And so we are just going to get the answer I said, obviously, unsurprisingly, since this is a well-established result. So why does that happen? Well, the answer is that near n equals 1, there's two contributions to order epsilon contributions to this thing. The first is that the n equals 1 plus epsilon, so that just gives us epsilon times this thing, but that's going to be cancelled out by the Z1 to the n term, okay? So that was something I said that was correct. But we also have a change that comes from the linear change in the metric G1n with respect to n as we go away from n equals 1, okay? And so what is that thing? Well, it's just epsilon times dg by dn times the change in the metric times the derivative of this Einstein-Hilbert action with respect to the change in the metric. Okay, so this should be implicitly treated as we're summing over metric indices here and also integrating over the manifold. Okay, and this term gives us exactly the same sort of thing. So the full thing is the derivative with respect to g of the Einstein-Hilbert action on G1 to the n minus the log of the matter partition function. Okay, and this is all evaluated at G1n equals G11, and this thing is evaluated at n equals 1. Okay? So it might seem this is pretty complicated because this thing we haven't controlled at all. We have no idea what it is. It's just some back reaction that happens when you go away from n equals 1. But magically, at n equals 1 and nowhere else, then these two terms are equal to 0. And so this is exactly equal to just log Z1. Okay? And so then this is just delta by delta g of log Z1 evaluated with the metric G11, but by definition, G11 is the saddle point of the partition function Z1, so this has to be equal to 0. Okay, so this is using the fact that the metric at n equals 1 is just a solution to the equations of motion with an action just given by this term and this term. Okay, so that's why this whole thing can be forgotten about. You don't have to worry about how the metric is changing as you go away from n equals 1. And the only remaining terms are these ones that we already calculated yesterday that just give minus epsilon times the generalized entropy. Okay, and that's the final answer we get. Okay, great. Any questions about that? Okay. Now let us switch back to evaporating black holes. So if you recall from the distant past of Monday's lecture, we argued that the essential features of having a black hole information problem is that we have a load of degrees of freedom, think of them as qubits, coming out here, where basically the number of qubits is much greater than the Bekenstein-Hawking entropy of the black hole, A over 4G. And these qubits are supposed to be roughly maximally entangled with stuff in the interior of the black hole. Okay? And so that makes it seem like their entanglement entropy is bigger than the Bekenstein-Hawking entropy of the black hole. But if the black hole is really described by a system of size, dimension e to the SBH, then there's just no way to fit all these degrees of freedom inside the black hole, which is against the idea that we have that we want this Hilbert space of black hole microstates to describe everything inside the black hole. Okay. So the idea, at least for most of this lecture, is we're going to take this setup, we're going to take the essential features. If we have more entanglement between outside the black hole and inside, then we feel like we should be allowed in the semi-classical geometry. And we're going to try and simplify the problem as much as we humanly can. As much as we can while still maintaining those essential features. Okay? So how do you simplify a problem in quantum gravity? Well, step one, it's a very standard strategy. Just want to reduce the number of dimensions. Okay? The more dimensions you have, the more degrees of freedom you have, the more nastier and worse behaved the gravitational path integral becomes. So we just want to go to as few dimensions as possible. Smallest number of dimensions that you can possibly have that has black holes. You can have 0 plus 1 dimensional quantum gravity, but it just describes the world lines of particles. It certainly doesn't have black holes in it. It is 1 plus 1 dimensions. 1 dimension of space, 1 dimension of time. There's a particularly simple theory of 1 plus 1 dimensional gravity that has become very popular in the last decade or so since it was understood. It's sort of, in a preferred way, arguably the simplest theory of 1 plus 1 dimensional quantum gravity, and that is called JT gravity. So I'm going to give you the action of JT gravity, just so you have it written down and you have something explicit in mind. But the details of this action will not be super important for anything I'm going to say. So the first thing we have is we have an Einstein-Hilbert term, integral over space-time manifold, square root of g times the Ricci scalar. And we have the usual Gibbons-Hawking-York boundary counter term, where h is the induced metric at the boundary of the space-time, and k is the extrinsic curvature. And the prefactor, normally we'd call 1 over 16 pi g or whatever, but in this case, for reasons that will become clear later, then it's more normal to call it S naught over 4g. Okay? So, in higher dimensions, we could be done here. We'd just say we have pure Einstein gravity, and that would be the simplest thing to do. In 2 dimensions, pure Einstein gravity is not a very sensible theory because it's actually over-constrained. So the Einstein tensor in 2 dimensions is essentially identically 0. And so if you want to put, let's say, matter in the theory, then you just can't solve it. If you don't want to put it, then the equation of motion is vacuous. So the standard thing one does in 1 + 1 dimensions is we add what's called a dilaton field, which is just a scalar field that couples to the Ricci scalar R. Okay? And this may seem like we're doing something weird and different that doesn't have a feature in higher dimensions. And so how do we know what we're doing is now analogous to higher dimensions? This scalar field should be thought of as representing in the 2-dimensional geometry the area of a transverse sphere. So if we have some spherically symmetric spacetime, say a black hole, this black hole over here, right? It almost looks 2-dimensional. We just sort of have a time direction going upwards and a radial direction going outwards. But there's an extra important degree of freedom, which is the area of the transverse sphere. So that's roughly constant on the horizon. It gets big out here at infinity. And it goes to 0 at the singularity. Okay? So if I do a dimensional reduction of higher dimensional gravity actions, I'm basically always going to get something like this, with this being the area of the transverse sphere, or coming from the area of the transverse sphere in higher dimensions. Okay? So in general, you also want to add some potential for the dilaton. In the case of JT gravity, you basically take the simplest potential in the dilaton for small fluctuations of it, so we just treat the potential as linear. Okay? Again, these details are not super important. This is just one concrete model to have in mind. The basically results we get are going to be pretty universal in any theory of gravity. But the normal potential to go with is this. And what this does is it, once we integrate over the dilaton, so this is sort of the only action the dilaton's going to have. It's going to impose a delta function that sets r equal to -2. Okay, so this is going to put us in anti-de Sitter space rather than any other boundary conditions. And then the final term we want is just, I think this should be a plus sign actually. Don't know why I wrote that. I think I was writing minus the action. This should be also complementary with a boundary term to make the variational problem well defined, which is again just the obvious thing. Phi times k. It's helpful to make it k minus 1. We're going to have boundary conditions where phi is held constant in the boundary, so this k, phi minus 1 is, the minus 1 term is really just a constant, but it makes the action finite. Okay? So don't worry, I really want to emphasize that you should not worry too much about the details of that action, but just so that it says it's written down, then yeah, that's what it is. But yeah, this is just the current fashionable, most popular theory of 2D gravity out there. And it's that for a reason. It is sort of the simplest one. Question? Yeah.
So just to make sure I understand correctly, so basically is the first line purely topological and the second one is the most interesting, more like dynamical part in some sense? Yeah,
exactly. So that's another way of saying why we need to have the dilaton is that the Einstein gravity action is topological. That's equivalent to what I just said. Basically, it doesn't depend on the metrics. It doesn't give you an interesting equation. Yeah, that's going to be important later, but yeah. Come back to it. Okay. Great. Okay, so then, this theory can describe black holes. It can describe, for example, two-sided wormholes where you have some infinite ADS-like boundary out here. You have a horizon for a black hole and a white hole, and you have another boundary out here. And you might think there's a singularity up here and down here. Technically, there isn't, because 2D gravity is sort of too simple to have singularities. You sort of have the equivalent of like a Reisner-Nordstrom singularity, where phi goes to minus infinity, going up here. But let's not worry about that. As I say, the singularity is not important to Hawking radiation. Hawking radiation is about stuff happening at the horizon, as we saw on Monday. So we'll just not worry too much about what happens there. But there is one thing about this, is that it's a two-sided black hole, and the information problem is sort of most naturally stated in terms of one-sided black holes. Okay? So what would we do on a one-sided black hole, at higher dimensions to make a one-sided black hole? Well, we'd imagine there's some origin of space-time here and some collapsing matter of a star, whatever. Yeah, and so what's happening here is that R is going to 0, and that means that the transverse dimensions compactify to the point, and so on. And that's what lets the space-time, the sort of radial direction, get cut off and come to an end. Okay? If we're in 1 + 1 dimensions, then we can't really do that, because there are no transverse dimensions. You have the dilaton field that can do whatever it does, but yeah, it can't sort of smooth off to a smooth point. So what we need to do to make a one-sided black hole is just add some degrees of freedom to our theory on which space-time can end. Okay? So these are called end-of-the-world branes. They were originally studied in sort of M theory and things like that. But let me use a different color. All it means in our context is we have this two-dimensional geometry, and then it just ends on some time-like surface. And that time-like surface that it can end on is just a dynamical object in the theory. Okay? So the end-of-the-world brane has some action, and the simplest action for it is just some constant mu that you can think of as the mass of the brane times the integral along the world line at the end of the world brane. Okay, so this just basically tells you that this end of the world brane goes along a geodesic. And we now have a one-sided black hole in our theory. Okay? Okay, so the next thing we need to add is some Hawking radiation. Okay, so the sort of realistic way to do that would be to add some matter fields to our theory, add a matter action, maybe some 2D matter CFT or something. We'll talk a bit about that towards the end of the lecture and how things work in that case. But for now, we're going to do something much stupider, because physics is the art of being as stupid as possible, but no more stupid. And all we're going to do is all we really care about here is that we have some degrees of freedom outside and degrees of freedom inside, and they're going to be entangled, and we have more entanglement than SBH. Okay? So what we're going to do is we're going to say, rather than having one type of end-of-the-world brane in our theory, we're going to have a lot of different types. We're going to call them I. So you can think of these as just like different species of particle. Okay, they're just different species of end-of-the-world brane. And then we can consider, so then there's a lot of different states of the black hole that you can call psi I that describe a black hole ending on an end-of-the-world brane of flavor of species I. Okay? And all we're going to do is to construct by hand. Okay, we're not going to have, with realistic black holes, you don't have to do anything. You just evolve forwards in time, and you end up with this huge amount of entanglement. Here, we're going to be much hackier. We're just going to construct by hand a state where the species of this end-of-the-world brane is going to be highly entangled with some just auxiliary reference system R. Okay, so it's not going to be in the space-time at all. It's just in a quantum computer or something outside the space-time. Okay, and that's going to represent a Hawking radiation at infinity. Okay, so we're just going to construct a state where these two things are entangled. So if we say there's k different species of end-of-the-world brane, then this is creating a state where semi-classically, this auxiliary system outside the space-time R is maximally entangled with the end-of-the-world brane, and the amount of entanglement is given by log k. Okay, k is can be thought of as some parameter of the theory, of our very stupid theory. And now we can just take k to be whatever we want, make it as big as we want, within the confines of this stupid theory. Again, there's reasons to say in a realistic model you shouldn't have that many flavors of particle, but we're just trying to make a stupid toy model that's going to let us see the calculations very nicely. And yep.
Yeah, so you said that the radiation is highly entangled with the end-of-the-world brane.
Yep.
So should I think of the end-of-the-world brane as having a certain number of degrees of freedom that I can entangle with the radiation, or?
Yeah, so I refer to them as different species of end-of-the-world brane. You can also think of it as internal degrees of freedom sitting on the end-of-the-world brane, like some finite dimensional quantum system that just sits on the end-of-the-world brane and is included as part of our theory. Those are mathematically equivalent statements.
Okay, so in some sense, each flavor gives you one bit of entanglement with the radiation.
It's not one bit, it's one state. Right, so the number of different flavors of end-of-the-world brane, if I have 2 to the n different flavors of end-of-the-world brane, then that basically gives me, is equivalent to having n degrees of freedom, n qubits sitting on the end-of-the-world brane. Right, if I have n qubits sitting on the end-of-the-world brane, I can make 2 to the n different states, orthogonal states at the end of the world.
Thank you.
Okay, great. Okay, so now, since we can make k be whatever we want, we can make it be much bigger than the Bekenstein-Hawkey entropy of the black hole, and then we'll have an information problem. We'll have more entanglement in the semi-classical geometry between the radiation and the interior of the black hole than is allowed, or that we think should be possible because of microstate counting. Okay, so one thing I should say is what is the Bekenstein-Hawkey entropy in JT gravity, because it should be area over 4G, but what is area here? Well, I said before that the role of area is played by this dilaton phi, right? That's the area of the transverse sphere, which would be the horizon area. Horizon area is the transverse sphere. So indeed, you can calculate that this is exactly 2 pi times the dilaton. If you look at the action up there, then you'll notice that, so that's coming from the phi r term. We also have the S naught term at the front, and that again looks like it's proportional to r. It sort of looks like it's shifting phi by a constant. And so indeed, we get S naught plus 2 pi phi is the full formula for the Bekenstein-Hawkey entropy, okay? So that's why I called that coefficient at the front there S naught, because it basically tells you the Bekenstein-Hawkey entropy when phi equals 0. Okay? So this can be derived using Euclidean calculations. There's a Euclidean derivation of the Bekenstein-Hawkey entropy, which you can think of as a very baby version of the derivation we did yesterday, where basically you construct the thermal density matrix and then take trace of rho thermal to the n, and then take the derivative with respect to n, n equals 1. And that's the thing you get. This thing is the term that pops up instead of the area of the extremal surface. Okay? It's much simpler actually because the thermal state you have the partition function preparing it isn't just Zn symmetric, it's actually U1 symmetric because it's just a Euclidean evolution by some time, and you can rotate through time. So that was actually done by Gibbons and Hawking decades before Lukowitz-Maldacena. Okay. Great. So I've sort of told you we want to study this state where this end-of-the-world brane is super entangled with some radiation, but I haven't told you anything about how on earth we make that state, right? This in the Lorentzian geometry, this end-of-the-world brane is just sitting behind the horizon. It's not like a particle I've thrown in or anything like that. So it shouldn't be obvious how we make the state, but it turns out we can very easily. We're going to make it in exactly the same way the states yesterday were being made. It's going to be prepared by Euclidean path integral. Okay? So if we take this geometry and we just analytically continue it, the Lorentzian two-sided wormhole would just become a disk. Okay? Euclidean Schwarzschild in higher dimensions has a topology that is a disk cross SD minus 2. So the sort of thermal Euclidean circle is contractible at the horizon of the Euclidean black hole. And so in this case, the S of d minus 2 is just a dilaton, and geometrically we just have the disk. Okay? We also have this end of the world brane sitting somewhere in the interior, so the sort of the slice where the Lorentzian geometry starts is the middle of the disk, and so we have an end of the world brane that on that slice is sitting somewhere there, and then that end of the world brane is just going to follow a geodesic. It's going to come out and hit the boundary somewhere there. Okay? So this part of the boundary doesn't actually exist in the end of the world brane Euclidean geometry. We just have part of a thermal circle and then ending on some end of the world brane. Okay? Okay. So we'd like to interpret this as a Euclidean path integral that's preparing a state, or rather really what this full Euclidean path integral is doing for us is it's computing the partition function on closed geometry is not computing a state, it's just computing a number, which we can think of as the inner product of psi I with itself. Okay, for an unnormalized version of psi I that is prepared by this Euclidean path integral. Okay, that's exactly the same thing we had last time, where we had a ket was being prepared by a hemisphere, a bra was being prepared by a hemisphere, and if you just glued them both together and integrated everything, you'd be finding the inner product of the state with itself. Okay? So we don't really want to be computing this. What we want is to be preparing the state psi I, and so to do that, we just erase the top half of this geometry, and so it's just going to be prepared by a partition function on this thing. Okay? So you should be a bit careful about what we mean by this. In a gravitational path integral, the geometry sitting in the interior is dynamical, right? So the only real things we're fixing are the boundary conditions at infinity. So what do I mean by drawing this? I mean that we're preparing a state using a Euclidean path integral with boundary conditions where we have a particular sort of defect here where an end of the world brane starts, have a boundary of an end of the world brane here, okay? And that defect, that boundary is labeled by I. Different values of I will correspond to different boundary conditions there. And then we just have some Euclidean boundary of a certain length that depends on the temperature of the black hole. Okay, so if you want to think of this as like in a boundary dual CFT, then this defect would just be a particular state in the boundary theory, and then we're evolving that state in Euclidean time. Any questions about that? Because this is a pretty important setup for the calculation. From here, it's basically just some maths.
Yeah, so confused about a few things. One is, it seems to me like this state should be characterized not only by I, but like by the geometry at the top or something like that. So,
well, it's okay. So we're wanting to consider a state where the semi-classical, you can't hold the semi-classical geometry fixed because the semi-classical geometry is just an approximation. But this is the sort of real state prepared by the boundary. That if I have some simple observable, maybe I compute some correlation functions of something here and something up here, so I've closed it off, then the saddle point geometry looks like that particular semi-classical geometry. So that's the only sense we ever have a real boundary, true quantum gravity state has a semi-classical dual. It just means that if you take some simple observables here and compute them using gravitational path integral, then the dominant saddle point has that semi-classical geometry. So compare it to the thermal field double state in CFT. Okay, the thermal field double state should just be thought of as the state that is prepared by a Euclidean path integral for time beta over 2. Okay, this gives us a state in HL tensor HR. But when we go to do bulk computations, they will be so we have expectation values in the thermal field double state. We have beta over 2 here, beta over 2 here. They will be dominated by the Euclidean Schwarzschild geometry. Okay, and if we have some Lorentzian time evolution here or something, then that will go into the Lorentzian part of the Schwarzschild geometry, and that's what it will describe.
I guess what makes me uncomfortable, maybe if you can explain this, it'll clarify my confusion. I would have expected for example, yesterday you were drawing these semis, like these hemispheres.
Yep.
I would have been more comfortable maybe with a cylinder where I'm also integrating over all the field configurations at the bottom of the cylinder. So why do we have this no boundary thing at the bottom?
So you mean you're asking about the hemispheres yesterday, or?
Yeah.
Yeah. So good. So let's say I'm just preparing vacuum ADS. Okay, I would prepare this. The vacuum state of the CFT can be prepared by an infinitely long Euclidean cylinder. Okay, but it turns out that is conformally equivalent. I just do a conformal rescaling to a hemisphere.
Perfect. Okay.
Okay. Yeah, if this is the state operator correspondence in CFTs. So the set of states are dual to the set of operators. So if I extracted a point out here, then this would be a infinite cylinder starting with some state. But then that state is just they're dual to the identity matrix. So we can just put an identity here, which just smooths out the hemisphere. That was maybe not very clear. The other way to say this is that Euclidean ADS has a boundary, conformal boundary that's the sphere. But those are equivalent statements.
Awesome. Thank you.
Again, just to make sure I understand correctly, so when you drew the Euclidean JT with brain picture,
yep.
So the horizon is at the center, is the origin of the disk, right?
Sorry, the horizon.
The horizon will be at the center, and we have
yep.
drawn the anode brain to the left because it's inside the interior, right?
Yep.
Behind the interior. Okay.
Yep.
Awesome.
And this follows from the equation of motion. If the end of the world brain has a positive tension, then yeah.
Yeah.
Well, actually, there's two solutions. One outside as well, I think, but the other one has large reactions, so it can be ignored.
Excuse me, can you repeat, please, where you put the defect? Just on the boundary, if I'm not mistaken, and why do you put it there?
Yeah. So whenever we do a path integral, right, the only things you're allowed to fix are boundary conditions, right? Everything else, every other dynamical degree of freedom gets integrated over. If we're doing a path integral in quantum field theory, you can also fix the geometry and so on, because those are background things that are fixed. They're not things that are dynamically being integrated over. In gravity, all the geometry and stuff in the middle, just all the degrees of freedom in the middle is just being dynamically integrated over. So the only things we're allowed to fix is what's happening out in the boundary. And then we can fix that in a way that is intended to prepare a certain state in the bulk, and will prepare a certain state in the bulk for the dominant saddle points for simple observables, but that's sort of all we can do. Like we can't really fix the geometry on a time slice. It doesn't make sense.
Basically our construction, you say.
Sorry, say that again?
You said that it's our construction, so we are making things like this because we want to write something.
This is like how quantum gravity works, right? States in quantum gravity, if you wanted to define quantum gravity using a path integral, all you can do is define a path integral with certain boundary conditions and say, the state you want is the state prepared by those boundary conditions. Maybe there's a better formulation, some sort of canonical formulation of quantum gravity that you could then do other stuff in, but if we only have path integrals, then that's all we can do. Yep.
How much Euclidean time you evolve the defect? Beta over 2 or less? Or?
It will be less in general, I think, because in the limit where the mass of this thing is very large, then it will be beta over 2 because this will sort of... So we want the temperature of the black hole is determined by the full size of this circle, right? If I make the tension, the mass at the end of the world brain really, really high, then it will go out to the boundary because it will want to be shorter. It has some large action, and it will just be a little thing like this, and then it will basically be beta over 2. But in general... it depends what you call, in general, this evolution will be shorter than beta over 2, if beta is the temperature of the black hole. Okay. Yep. Say that again.
Did you restrict to time reflection symmetric geometries
Yes,
and
so
reflection symmetric path integrals?
Yes. So this is being prepared by a Euclidean geometry. That's a nice thing about it, which means it has to be time reflection symmetric because that's what Euclidean path integrals can prepare. The great thing about that is I can draw two-dimensional Euclidean geometries on the board. I can't draw complex geometries for the life of me. I'm not sure anyone can. I don't even think that's my artistic abilities limiting me. So that's going to make it much easier to diagrammatically draw things. But in general, for realistic things, you want to have Lorentzian time evolution that's going to make the black hole evaporate, and then you're going to have some complex geometry. But the general arguments will still go through. Yeah.
Jeff,
Yep.
one more question. So Nico was asking about why we can draw this as a hemisphere instead of an infinite cylinder. You said it's a conformal transformation. And this is thanks to the fact that this is a CFT that we're dealing with, right? Would we then have expected that to have the ADS-CFT correspondence? Like, we needed a CFT itself because yesterday we were saying that we got this from this path integral on the boundary, we got a path integral in the bulk, but in the bulk, of course, we have more like the Hartle-Hawking no boundary path integral is what we're getting, a sphere. Like, would we have then expected that we needed a hemisphere to start with in the bulk to then get a hemisphere filled in for the path integral in the bulk?
Yeah, so for the Hartle-Hawking no boundary state, then the bulk is a sphere rather than the boundary being a sphere and the bulk is a ball, right? And so it has no boundary, and so that's a pretty different setup. But it is true that Euclidean ADS has a conformal boundary that is a sphere, and more importantly, the real reason you need a CFT on the boundary is that the asymptotic symmetry group of ADS is exactly the conformal group. So that basically tells you that the only thing that's really meaningful is the conformal metric at infinity. Otherwise, you'll have some cutoff dependent thing that won't make sense. So it is. I think the answer is that you're right. The fact that we're able to go, it's sort of crucial that we have a CFT on the boundary so that we can go between cylinders and spheres and so on. But that's because we can also do that in the bulk. And so there wouldn't be a matching between two sides if we weren't able to do it on the boundary. Okay, anyone else? Great. Cool. Okay, so this is how we're going to prepare state psi I. And now we have a setup where we think we have a paradox, but we can just go ahead and we can explicitly compute the entanglement entropy of this radiation system R and see what it is, and see whether indeed we have a paradox, indeed it ends up bigger than the Bekenstein-Hawking entropy or not. Okay? And we now know how to compute entanglement entropies using path integrals. We just define it as minus the derivative of trace rho r to the n. Okay? And that's going to let us get the answer we want. So it turns out it's actually simpler to start by not computing this for arbitrary n and analytically continuing. We'll do that in a minute. But let's just think about the simplest n that's not 1, which is n equals 2. Okay? And the trace of the density matrix squared is a quantity that's called the purity. It's also equal to minus what's called the second, e to the minus the second Rayleigh entropy of the radiation system R. Okay, that's just a definition of the second Rayleigh entropy, but some of you might have heard of that, but not of the purity. But the key point is that morally, we want to say that this is roughly e to the minus the Bekenstein-Hawking entropy. Okay, it's not actually going to be that. In general, it's always bigger than that. The second Rayleigh entropy is always smaller than the Bekenstein-Hawking entropy. But for a maximally mixed state, then they're equal to one another. So if all the eigenvalues of this thing are really small, then they should keep getting small. And in particular, if the sort of naive semi-classical answer is right, that this thing looks like it's maximally mixed because it's maximally entangled with something over here, then the von Neumann entropy should be log k, and this should indeed just be 1 over k. Okay? So that's the answer Hawking would have confidently given, but we want to be a bit more careful and actually compute it ourselves. Okay. So the first thing we need to know is what the density matrix rho r of this state up there is. So we have rho r is just the trace over B of sum over I. I should have had a normalization factor here. 1 over square root k, okay, and I want these psi i's to be normalized. That will then make this a normalized state, which is what we want. Sum over I, psi I, and then we have a bra, sum over j, psi j, j, okay, and then we get two factors of 1 over square root k here. So this gives us 1 over k at the front. So then this whole thing, the partial trace is trivial. It just gives us an inner product of the psi I and the psi j. So we get sum over I j, psi j, psi I, ket I, ket j. Okay? So this is telling us the reduced density matrix on R in terms of these matrix elements, ket I bra j. And then we just need to compute trace of rho r squared. And the trace of a density matrix squared is just, we have a 1 over k squared at the front. We technically should have, we have two copies of the density matrix, so we have I, j, k, and l. But j is going to be set equal to k by the fact that we're taking a product, and then l is going to be set equal to I by the fact that we're taking a trace. So we end up with just sum over I and j of rho j I, rho I j. So that's just the inner product of psi j, psi I, modulus squared. This should be a 1 over k squared, because we have two factors of 1 over k. Okay? So this is some formula that's very explicit, and we've written it in terms of these things that we know how to compute using Euclidean path integrals. Okay? So let's just do that. Okay, so psi I, psi j looks like Euclidean path integral where we have some defect in the state I down here and one in the state j up there. And then we have two copies of this. Okay? And then we need to sum over I and j and get a 1 over k squared. And also we need to make sure that these psi i's and psi j's are normalized. So we need to divide through by this thing squared. Okay? This just, we have, this thing gives psi I, so it gives the square of the normalization of psi I, and there's 4 psi's that need to be normalized here. Okay. So let's first what we want to do is look for saddle points with these boundary conditions, okay? And in quantum gravity, we want everything to be dynamical except the boundary conditions. So we want not only those saddle points to be allowed to have any geometry that's going to satisfy our equation of motion, they should also be allowed to have any topology, okay? So this is going to lead to 2 possible saddle points. Well, actually, let's first compute this thing down here. Okay, so the dominant saddle point for this thing is obviously just going to be the Euclidean black hole. We know what that is. And so we should work out what the action of this thing is. Okay, so this is just some gravitational action. And I've now erased my action for JT gravity, which is annoying. But the important part, and the only part I'm going to care about, is just the Einstein-Hilbert term plus boundary condition, which is S over 4 pi integral square root GR over M plus integral over the boundary of M of square root H K. Okay, so as someone, I can't remember who now, stated earlier, this is what's called a topological action, which means for any geometry of on a given topology, this is actually a particular constant number. Okay, it doesn't depend on the geometry at all. It only depends on the topology. So this is something called the Gauss-Bonnet theorem. If you ever do a topology course, how do I spell Bonnet? I think like that. If you ever do a topology course, you'll see it. It's a very beautiful little result. But yeah, that's the answer. And so this action ends up being equal to minus S0 times what's called chi. Okay, so chi here is the Euler characteristic of the 2D manifold. It's very badly written. But in particular, chi is equal for any 2D manifold to 2 minus the number of boundaries to that manifold, the number of boundary components, minus 2 times the number of handles. Okay, so a handle is just like, take something and make a little connection through here. So as an example, for a sphere, we have no boundaries and we have no handles, so the Euler characteristic is just 2. For a disk, we have 1 boundary and no handles, so the Euler characteristic is 1. For a torus, say we have 1 handle and no boundaries, so the Euler characteristic is 0. Okay? Okay, so in this case, we have the disk, and so the disk has Euler characteristic of 1, so this action is minus S0, which means this thing is just e to the 2 S0. Okay? So that's that normalization factor out the way. I'll keep this up here, and S equals minus S0 chi for memory. Okay, so now we need to worry about this thing up here. And here's where it turns out that there's 2 possible topologies that can be relevant. The obvious one is that we can just have 2 copies of the saddle point down here.
Geoff?
Yep.
Do the contributions from the end of world brain and the dilettante and the action cancel? Do we not? Are they subleading?
Yeah, they're subleading. So I'm just taking the limit here where S0 is really big, and everything else I'm going to ignore for the purposes of these computations, just to get a first guess.
Okay.
Yeah. Okay. So, what do we get here? Well, first thing to note is that we have 2 disks. Each of them gives a factor of e to the S0. We just worked that out. So that gives us an e to the S2 S0. Of course, that's just cancelled by the e to the 2 S0 on the bottom. It's unsurprising because we have the same, we have 2 copies of this geometry on the bottom and we have 2 on the top, so they give exactly the same thing. Okay, but we also need to look at these i's and j's and the fact that we're summing over these things. So you'll notice that here we have an end of the world brain starting in state I, and ending up over here in state j. Okay? So that's going to give us a factor of delta ij, because the end of the world brane needs to be in the same state in both cases. Okay? So this gives us delta ij, and then we sum over I and j separately. Means we get one factor of k when we do that sum. It just comes from the diagonal pieces. So we have one factor of k from the sum. We have a 1 over k squared out the front. And so this whole thing gives us a 1 over k. Okay, so these two things cancel. In fact, they exactly cancel even if we'd included the other terms in the action. And so we get 1 over k, which is indeed what we claim should be the case when k is much less than e to the Bekenstein-Hawking entropy, or what Hawking would claim to be the case always. Okay, so in fact, in that case, when k is much less than e to the s naught, then indeed this is the dominant contribution to the path integral. But if we make k really, really, really stupendously big, then it stops being dominant, because this 1 over k here means that it just goes away to 0, right? It gets smaller and smaller contribution until it eventually goes to 0. And it turns out there's another geometry that is not suppressed by any factors of k, and so can become larger once this thing is sufficiently small. And that's very simple. It's the two black holes connected together by a wormhole. So there's a wormhole, which in this case is just a strip ending on the two end of the world branes. And you'll see that now this end of the world brane in state I is connected to another end of the world brane in state I, whereas j is connected to j, and there's no longer any reason that I and j have to be equal for this to give a non-zero answer. Okay? So that means that unlike the two black hole answer, now this double sum over I and j gives us not just a factor of k, but a factor of k squared. That exactly cancels out this 1 over k squared, and we no longer have a 1 over k down here. Okay? So this is an extra contribution to the full answer. So we had the 1 over k from before, but we also have this extra thing. Has no factors of 1 over k, but topologically, this thing is just one disk now rather than two disks, because the two disks connect together. That means it only gives us one factor of e to the s naught. We have two factors of the s naught on the bottom, and so this whole thing gives an e to the minus s naught. Okay, so the gravitational action, the classical action of this thing means that it's really suppressed because we want to take s naught really big. That's semi-classical limit. You can think of this as like some sort of gravitational instanton effect. It's some tiny Euclidean contribution to the action. But even though it's really tiny, if we make k sufficiently big, then this thing gets bigger than this thing. Okay? So that's great, because way back in the day, I said that the Bekenstein-Hawking entropy was equal to S naught plus some dilaton contribution that we want to think of as subleading. So this is saying that indeed, no matter how big we make k, the Rainy 2 entropy, the purity, is not decaying forever. And so it sort of looks like it's saturating at something around the Bekenstein-Hawking entropy of the black hole. Okay? I could have included the subleading contributions from the dilaton part of the action and so on. I would get some answer that's just the answer that it is. I would not have got the Bekenstein-Hawking entropy. The subleading corrections will not be equal to those of the Bekenstein-Hawking entropy. That's fine, because I'm not computing the entanglement entropy of the radiation yet, right? I'm computing the Rainy 2 entropy, which is it's a much less accurate quantity. It's a much less good quantity. Yep.
I don't see why it's legal to connect the I with the I and the J with the J in that way. Like looking at the right hand, like at the right board at the very bottom equation. Like from that, I would naively think, okay, I should connect the I with the J.
Well, we're just doing path integral, and the gravitational path integral says that we can do anything we want here. Okay, here is I think the observation you're making. Let's say we only had one copy of psi ij. Okay, then we would have said, well, we only have one boundary, and the only place this can go is to connect it to the j. Okay, and so it has to connect I to j. And so this is suggesting that when I is not equal to j, or in fact always, then The modulus of psi I psi j squared is not equal to the square of the answer we'd get if we just computed psi I psi j. Okay?
Is there also a contribution connecting the top left j to the bottom right I and the bottom left I to the top right j?
Yeah, that depends on whether you want to think of these end-of-the-world branes as oriented or not. So if they have a direction, then you'll notice, because this is a modulus squared, then if the end-of-the-world brane is meant to sort of start here and go inwards here, then it will come outwards here because it's a bra rather than a ket, and vice versa. And similarly, inwards here, outwards here. So the two contributions I showed are allowed under that. The one where we connect this to this would be not allowed if you impose that constraint. If you have a different theory where the end-of-the-world brane is sort of its own antiparticle, if you will, then that is allowed. Those are just two different theories. They have slightly different joules. Yeah, it's always subleading anyway, so it doesn't really matter for the points we care about, right? Because that one both has to have I equal j, so it gets suppressed by 1 over k, and it's one disk rather than two disks, so it's suppressed by e to the minus s naught. So it's just always really suppressed compared to everything else. It's not an interesting contribution. But you can include it if you want. Yeah, so this should be making us very suspicious that we think we're doing reasonable rules. We're computing what we thought was the square of something, and then we got the answer that isn't the same as if we just computed this one thing on its own. So the answer in this simple theory for what's going on here is that it turns out what this gravitational theory is computing is an average over a whole ensemble of theories. I don't want to get too much into that because it could be an entire lecture series on its own, but that's really what it's doing. And the expectation of a square of an average, the expectation of something squared is not the same as the expectation of that thing squared. So in particular, there is a boundary joule to this theory that is an ensemble joule. It's averaged over a whole ensemble of theories. And in that joule, then this thing looks like, for I not equal, looks like there's a delta ij plus something that's roughly e to the minus s naught. It's a bit different to that, but never mind. Times rij, where rij is an independently drawn Gaussian number with mean 0 and variance 1 for each pair ij. Okay? So if you compute the expectation of this thing, you average over those rij's, you'll just get delta ij. But if we compute the modulus squared of it, then we get an extra contribution that comes from this thing. I'll maybe have time to talk briefly about, in more realistic theories of quantum gravity, then it is an open question whether there's the same sort of ensemble averaging going on. In n equals 4 CP_MOs, we think there isn't. But in more realistic theories of quantum gravity, we also can't compute any of these things exactly. And that means roughly the noise in the computation means that this thing squared could actually be equal to the individual thing squared. We just aren't able to compute either of them. So that is an open question, but in this model, we know exactly what's happening, and it's this.
Sorry, question.
Yep.
Is there any limit or any way that the other parts of the action sort of match the e to the minus s, like they're of the order e to the s naught, so that becomes sort of order 1 correction?
Yes, so we normally take the limit. They can be computed explicitly. I'm just not doing so because I'm lazy. But we normally take a limit where S naught is parametrically larger than anything else. That's actually if you want to get JT gravity as a low energy limit of some high dimensional, it's a dimensional reduction of some high dimensional theory, that's the natural limit that you get it. You can think of it as like taking G to 0. The S naught looks like 1 over G. It's the thing that appears in front of the Einstein-Hilbert action. So yeah. You would have to care about that, but the answer would still be qualitatively the same.
Okay, thank you.
Okay. Yep.
One question I have is stability something that we should ever worry about? For example, that saddle may not be a solution to classical gravity, or like more complicated ones. So what are the rules of the game here? Like, should we just fill in however we can, or should it be like an actual feasible solution, or what?
In the case of this theory, we can actually do the full gravitational path integral exactly, or we can define it in a non-perturbable way, and we can do the complete path integral, and we get the same answer as this. In more complicated theories, we obviously can't. We just have saddle points, and we're sort of guessing somewhat and assuming that we can approximate things by saddle points. Okay, so as I say, this trace of rho squared quantity on its own does not get you exactly the Bekenstein-Hawking entropy, so it's not quite the page curve. It's something that looks very, very similar to it. But we wouldn't expect it to. But the thing we would expect to exactly obey the page curve is the actual entanglement entropy minus the derivative of trace rho to the n at n equals 1. Okay? So to understand this, we need to understand the case for n greater than 2, all the different integers, and then we'll hope to analytically continue, like we did last time. So I'm just going to draw, this looks like with, say, n equals 4. We have 4 boundaries, and we have a load of matching conditions here. So I1 here, I1, I2, I2, I3, I3, I4, I4, and these are all getting summed over. Yeah, I'll just call this IN. I drew 4, but you should think of that as being n here. And we have a 1 over k to the n. And then we have a normalization by n copies of that thing. So there's a e to the ns0. Because that's just we just compute that answer and take it to the power n. So that's easy. Okay. So I'll just briefly tell you, in general, there are a lot more topologies that can end up being relevant when k is roughly comparable in size to e to the s0. There is a way to do the full sum over all the relevant ones and analytically continue it and so on. You can read about that in the paper that introduced this model, which was replica wormholes, and the West Coast replica wormholes paper. It was me, Stanford, Schenker, and Yang. But if we either have k much less than e to the s0 or much, much bigger than e to the s0, then it's just one simple family of saddles that ends up dominating this thing. Okay? So if k is small, then we just end up with n independent Euclidean black holes. Okay? Each of those gives an action that, let's call this z1 to the n rather than e to the s0, because I want to be a bit more precise now. Each of these gives a classical action that's just exactly equal to z1. Right? So the gravitational action between top and bottom exactly cancels because we have same geometries on top and bottom. So that goes away. But we also have that I1 is equal to I2, I2 is equal to I3, I3 to I4, so on all the way around to n. Okay, so this sum over n degrees of freedom ends up just being over 1, just gives us one factor of k. This gives us 1 over k to the n minus 1, exactly. That's an analytic formula in n, so we can continue it, take the derivative at n equals 1, and we get s r equals log k. Okay. If k is really, really, really big, on the other hand, so that's the first half of the page curve. That's the Hawking part of the page curve, the easy answer. If k is really, really big, then we expect that we're after the page time. So that should be the opposite answer. And in this case, the leading thing is just the leading geometry that lets all these INs be independent of one another. Okay, so we have to match up this IN with this IN, this one with this one, this one with this one, this one with this one. The whole thing looks like a sort of pinwheel geometry with all these different Euclidean boundaries all connected together by one n-boundary wormhole. Okay? So in this case, the 1 over k to the n gets cancelled out by this sum because all these things are now independent. So we get something that is independent of k. But we have an action. The action looks like, I'll call it Zn. It's the classical gravitational, it's e to the minus classical gravitational action of this multi-boundary thing. And of course, we had a Z1 to the n on the bottom. This looks an awful, awful, awful lot like all the computations that we were doing yesterday, right? We have some Zn symmetric geometry here, And then we want to take Zn over Z1 to the n, and then analytically continue to n goes to close to 1. And indeed, we can see very explicitly here, if we quotient this by the Zn symmetry, so we just look at one of these n wedges, then we get a geometry that looks roughly like the single Euclidean black hole, except that there's a branch cut starting at a conical singularity here, that's this fixed point of the Zn symmetry, okay, that then extends, use red, extends all the way to the end of the world brain. Okay, so we go in a little loop around this conical singularity, then we end up at the next sheet over. We've actually gone from here all the way up to here, and we've ended up on this sheet. Okay, this is exactly the same setup we had last time. And as we argued then if we take the limit, n goes very close to 1, then this geometry basically becomes the ordinary Euclidean black hole. Okay, the geometry is unbiac reacted. We just have a very weak conical singularity getting here, and that conical singularity will end up converging to an extremum of the area, which in this case is just a bifurcation surface, right? If we look in this original geometry, we have a bifurcation surface here that's an extremum of area.
I'm very lost now. So can't we say the same thing for the above one? Like it has a Z2 symmetry, but we just treated it as a disk, but the bottom one we're treating it as...
yeah, because now we're wanting to analytically continue in n. That one we just computed at n equals 2. Now we have a whole family in n, and we want to be able to go to non-integer n. How do we go to non-integer n? Even though that geometry is not well defined at non-integer n, we look at the quotient geometry instead. That's exactly what we did yesterday, right? The quotient geometry has a conical singularity thing here. It has some action, and we made very, very general arguments yesterday that in the limit n goes to 1, n equals 1 plus epsilon, then this thing is just equal to 1 minus epsilon times the area of the point where this branch cut starts, right? Which is just the area of the bifurcation surface over 4G.
So in the top case, I could also do this mod out by Z2, get a conical singularity, and do it in this way?
So in the top case, we just have n fixed equal to 2. Yeah, you could have just worked out the action, but because we're not going to n close to 1, we won't get a simple formula like this.
Sure.
But I could have computed, going to the quotient geometry is just a way of rewriting the same calculation, right?
Yeah.
That allows us to analytically continue that calculation to n away from integers.
And is it possible to connect the i's in more funny ways where you get non-zero genus and sort of competing e to the minus s and 1 over k factors? As you start to increase the genus, I'm guessing that you get more e to the s.
So you mean so we reduce the number of the factors of 1 over k, but cost, say you can imagine that we have a wormhole connecting these two, but then these two are disconnected, something like that. Yeah, so as I said, when k and e to the s naught are comparable in size, one isn't vastly larger than the other, then that will compete at the same order as this pinwheel geometry and as the completely disconnected thing. You have a whole set of different things. The number of topologies in that set grows with n, and it's a much more complicated situation. It turns out in that model you can whack at it with some tools from free probability theory and some recursion relations and stuff, and I encourage you to read the discussion in the paper of how to do that, but it's a much more complicated situation, and I'm not going to talk about how to do it.
Cool. Thank you so much.
But you only care about that at the sort of transition from before the page time to after the page time. Okay. Okay. So we know from all the stuff we did yesterday that if we take the limit where n's close to 1, all we get is a contribution from the area of the bifurcation surface, and if we had any matter fields, we'd also have an entanglement entry of the matter fields, but we don't. Okay? So we get the answer that's just the area of the bifurcation surface, which is indeed, really this is equal to S0 plus 2 pi phi. In the JT gravity computation, that's what shows up instead of the area. Okay, so let's just go back to this situation down here. Should now realize that all this mucking about with wormholes, at the end of the day, was just reproducing Lukowitz-Maldacena. Okay, because that's if we're just interested in computing S of R, then all that ended up happening was the area of some particular surface in the unback reacted geometry. So we could have just computed this thing just by directly looking at this black hole and looking for extremum of area plus entanglement entropy, which in this case, because we have no bulk fields, just entanglement entropy, and then finding the one that has the smallest generalized entropy. So let's just do that and see how it matches with all the calculations we just did. Okay? So there's really 2 possible surfaces that are extremum of area here. The first is that the surface gamma is just the empty set. So there's no surface at all. Okay? So in that case, in that case, the area of the surface is 0, okay? But we have an entanglement entropy across the surface. And that's because the entanglement entropy that shows up is the entanglement entropy of everything that goes through the branch cut. And even if the sort of surface is empty, so there's no branch cut here, then by construction, the matter in R went through the branch cut, right? Because when we did trace of rho R to the n, then we glued, you can think of this here as this I1 did not get matched to this an I1 down here. Instead, this is set equal to an I1 over here. Okay, so you can think of that as the radiation is going through a branch cut that connects it in the ket on one sheet to the bra on the next sheet over. So this would just give us the sort of semi-classical entanglement entropy of the radiation, log K. The other option is that the surface is the bifurcation surface of the black hole, okay? And then we have a branch cut that extends from the bifurcation surface to the end of the world brane, okay? So in that case, the area is just the Bekenstein-Hawkey entropy. Then we also have to include the entanglement entropy of everything that went through the branch cut. But now not only did R go through the branch cut, but the end of the world brane did as well. Okay, so it's now the combined entanglement entropy of the radiation and the end of the world brane. But those combined are just in a pure state, okay, because they're just maximally entangled with one another. So this is just 0, and we get it's given by the minimum of log K and the Bekenstein-Hawkey entropy. Okay, so this is just the page curve. Okay, so we have successfully derived the page curve in this very, very, very stupid model. So I probably have, 15 minutes left. So what I now want to explain to you is, let's go away from this incredibly stupid model, talk about what happens in more realistic situations. The answer is that things get a lot harder to compute, but the intuitive story remains exactly the same. Okay. So let's just write down this rule in the careful way. It really is just the QES prescription we were talking about yesterday, but we're doing it in a slightly different context, where we're computing the entropy of some radiation rather than a part of the boundary, so it's worth writing. So the rule is that S of R should be equal to the min over extremal surfaces, gamma, okay? And before, we had the branch cut in the bulk had to end somewhere on the boundary. It had to touch the region big B on the boundary that we were computing the entanglement entropy of. But now nothing on the boundary goes through the branch cut. The only thing that goes through the branch cut is the radiation. Okay? So that means that if part of the bulk goes through the branch cut, then it has to be some compact region. It can't be anything that goes off to asymptotic infinity. So that means that gamma has to be the boundary of some compact region that'll be. Okay? And then we get a contribution to the entanglement entropy. It's just A gamma over 4G. And then we have a contribution from the entanglement entropy in the bulk semi-classical geometry that consists of everything that goes through the branch cut. What goes through the branch cut? It's the stuff in little b, together with the radiation system R that we could control where it went, and we made it go through the branch cut because we wanted to compute its entropy. Okay, so it's entropy of B and R. So in this context, this is often called the island rule. But it's really just the same as the QES prescription that we know and love, just for computing a different thing. It's computing an external system that's outside of your holographic theory rather than computing a boundary region of the holographic theory. Okay, it's worth just taking a second to clarify. People often get confused. So if B is empty, then we have an S bulk of just R, right? The semi-classical entropy of just the region R. And then we also have this entropy of the region R on the left. But if the actual minimum extremal thing has B not be empty, then those two things are not equal to each other. Okay? So just to be precise about what these two different things mean, this one is the actual entropy of the system R, given that we have a theory of quantum gravity. Okay? And it's entangled with some stuff inside the black hole in theory of quantum gravity. This thing is just a mathematical convenience for doing calculation. It's not a real physical entropy. It's what would the entropy be if we were actually working in QFT and curved spacetime rather than in quantum gravity. Okay, so we imagine if we had the saddle point geometry of the quantum gravity theory, but geometry was not dynamical, it was fixed, we were just doing QFT and curved spacetime, we have no Bekenstein-Hawkey entropy, anything like that, then we have an entropy that would be the answer, and we can use that mathematically, because of these computations using wormholes, to find the actual answer. Okay? Okay, so let's just briefly see how this is applied in sort of more realistic setups. So what normally people do, it's sort of most concrete to do, is to imagine a black hole in ADS, because ADS provides nice boundary conditions. This is not, the ADS here is just like a nice IR cutoff on your theory. Really the computation does go through in flat space, it's just less clean boundary conditions and so on. So we have some black hole here, formed from, say, some collapsing star or whatever it might be. And then we have some radiation. And the thing about ADS space is that usually when we study stuff in anti-de Sitter space, we impose what's called reflecting boundary conditions. Okay, so this means that when the radiation hits the edge of ADS, gets reflected back in and falls back in the black hole. This is why black holes do not actually evaporate in ADS unless they're very, very small. It's why energy is conserved in the boundary, right? If this stuff just sort of disappeared and didn't go back in, then energy wouldn't be being conserved. But this is a choice of the theory. It's a choice in the bulk. We can instead attach some QFT in flat space, just maybe some free theory or something like that. This is called the bath. And we couple these two things together so that the radiation can just pass straight through, comes out of the gravitational theory and straight into the bath. Okay, so from a CFT point of view, what we're doing is we're just coupling this CFT to the bath, QFT, in such a way that energy will leak out over time. Okay, so then we could get the black hole will now evaporate because it loses energy to the bath. let it do that for a while, let it do that. Eventually, at some late time, we have a load of Hawking radiation in the bath, and this is a very concrete setup where, now it's just in principle, it's in some quantum field theory, and we should be able to compute its entropy, and we'll either get the page curve or we won't get the page curve. In fact, we know from the CFT side that we must get the page curve because we know what the entanglement spectrum of the QFT looks like, and we know what the energy is, and so on. But we'd like to derive that from the ADS side. Okay? So we have some late time slice of the bath that starts up here, and we want to compute its entropy, and we're just going to compute it using this rule here. Okay? So in principle, this is still coming from exactly the same sort of wormhole computations we had before, but we just realized that all that work we did about computing the wormholes for each different value of n and so on, when we ended up analytically continuing to n equals 1, which is what we want to compute the entanglement entropy, we just ended up reproducing the QES prescription. Okay, so we just produced this thing, and the wormhole is just telling you that if you have a branch cut that is a compact region, then that corresponds to having a wormhole. It creates a wormhole. Okay, so then we just have to look for surfaces that are extrema of this thing. Again, there's two of them. There's two of them before the page time. There's two of them after the page time. One of them is just gamma is the empty set, again. Okay, so in this case, B is empty, so we just have area as 0, so we just have that the entropy of the radiation is equal to the entropy it would be if we just had a QFT in curved spacetime. Okay, so this is exactly Hawking's answer. SR equals S Hawking. There's another QES that sort of sits near the horizon of the black hole, just like in the JT gravity toy model. Some surface that's roughly here. Okay, so in this case, the branch cut, the region that goes through the branch cut, which is normally called the island, consists of everything down here. Okay, and in particular, it includes all the interior partners of the Hawking radiation. So let's call this gamma equals gamma horizon. That would give an answer for the entropy of the radiation that roughly gives an A horizon over 4G plus S bulk of all this radiation plus all this stuff in the island that also goes through the branch cut. Okay, and so what is the entropy of all that stuff? Well, again, we just have a load of entanglement between stuff in here and stuff in here, but the overall state has a pretty small entanglement entropy on that entire region. Okay, so that ends up just being, in fact, some order 1 thing that is not terribly important. And so if we see that whichever one of these is smaller is the one that gives the right answer, so this gives us exactly the page curve. Before the page time, this one's dominant. After the page time, this one's dominant. Okay, so one sort of subtlety here versus the very stupid toy model is that in this space-time, well, in the toy model, the extremal surface was literally just classical, okay? It was an extremum of area, there was no entropy around. If you actually look in this whole space-time, then there's no extremal surface of classical area. This is why, basically, that people didn't notice the existence of this quantum extremal surface until 2019, is at the time, everyone thought a quantum extremal surface would always be right next to a classical extremal surface. But here we have no classical extremal surface, but we do have a quantum extremal surface. Okay? So in particular, any surface in the bulk, if I go up and to the right, I perturb it in a forwards and outwards direction, then the area will get smaller if we're inside the horizon. It will get bigger outside the horizon. It's unsurprising that somewhere near the horizon, basically almost on the horizon, the expansion of the area in that direction is 0. And there's corrections to that when you include the entropy of the bulk fields, but basically still ends up being the case that somewhere close to the horizon, there will always be a surface that has 0 expansion in this direction. Okay? 0 expansion of the generalized entropy, including classical plus quantum. The confusing thing is that if we just include the classical area piece, then going outwards this direction always makes the area bigger, and so that's why you can't ever have a surface that's actually extremum, that the change is 0 no matter which way you perturb it. Okay. So how is this, why does this change when we have a quantum correction? Well, let's imagine we have two regions, call them A and B. In general, there's some modes in here, some outgoing modes that are included that are to the right of A but are not to the right of B. Okay? So that means the entanglement entropy across A for gamma A is generally going to be bigger than the entanglement entropy for gamma B. Okay? There'll be some order 1 difference there. This can be explicitly computed in 2 dimensions with the conformal field theory. In higher dimensions, it's more complicated, but it's some answer. But unfortunately, the problem is that the area of B is bigger than the area of A. So that means when we add the 1 over 4g and g is really small, it seems like this thing's going to be much, much bigger than this thing, and it's always going to dominate over this thing. Okay? So the trick is to imagine moving A and B further back in time. Let's call them A prime and B prime. So I'm just parallel transporting them backwards along the light ray. Okay? So the same modes that were in A but not in B are in A prime but not in B prime. Right? So roughly speaking, the difference delta S between this thing and this thing is going to be constant. It's going to be the same for A prime and B prime as it was for A and B. As we move backwards in time, it always stays the same. On the other hand, if I go backwards along a light ray, something near the horizon, it actually gets exponentially close to the horizon in terms of the radial coordinate r. So the difference in areas between these two things gets exponentially smaller as I go backwards in time. In fact, it decays, let's call this delta A, this thing, if delta t is the distance between my time up here and the time up here at which we're computing S of r, and the time at which a light ray coming from these things will go back and hit the boundary, then we find that the difference in areas between A prime and B prime, so we go backwards in time, is order e to the minus 2 pi delta t over beta. Okay? That means if we make delta t big enough, if we go far enough back in time, this area difference will become order 1, and then in fact smaller on order 1. And so that means we'll switch from having the generalized entropy of B being bigger than the generalized entropy of A to the generalized entropy of A prime being bigger than the generalized entropy of B prime. Okay? At some point, there'll be a point where they're exactly equal in generalized entropy, and that's the point where you have some quantum extremal surface. Okay, so when does that happen? Roughly, well, we want delta A over 4g to be order 1, which means that this thing has to be order g, which means that delta t has to be order beta over 2 pi log 1 over g, or equivalently, let's make it log of a dimensionless quantity, log of the Bekenstein-Hawking entropy of the black hole. Okay? So what this tells you is that the edge of this region with the branch cut, if I want to successfully make it into the region with the branch cut, I have to have jumped in to the black hole at least this time delta t before we're computing the entanglement entropy of the radiation. Okay? If you remember from Monday's lecture, this is exactly what's called the scrambling time of the black hole. Okay? So this tells us that if we threw some Dari into the black hole after the page time, exactly more than the scrambling time in the past, then the entropy of that Dari will now contribute to the entropy of the radiation, right? And if the Dari is maximally entangled with something that wasn't thrown into the black hole, then that thing that wasn't thrown in the black hole will now be maximally entangled with the Hawking radiation. This is exactly the Hayden-Preskel conjecture. The information thrown into the black hole after the page time comes out after exactly the scrambling time, beta over 2 pi log s. Okay, so that was a high-level summary, but I just want to give you some sense that these calculations give you more than just a page curve. They give you something deeper. Yeah, I think I'm already slightly over on time, so I'm just gonna leave that there, and that is me done. You are finally free of me.
Thank you very much. Do you have more questions?
Yeah. So is the two questions, I think, probably quick. Is that correct intuition for your previous toy model that if I try to hide too much stuff behind a black hole, eventually the black hole is no longer actually hiding that stuff and it's sort of outside of it? Like if I have too many underworld brains, they're actually not behind the black hole.
You could imagine that if you think of the end of the world brains as carrying a load of qubits, right? And well, you say say all but one of those qubits you thought were maximally entangled with some stuff outside, and then there was one sitting in some state, and you wanted that state to be secret, and you think no one can access it because because it's hidden inside the black hole. That's exactly like this Dari situation here, right? If something's maximally entangled with that one extra qubit, it actually ends up being maximally entangled with the radiation. That extra qubit is encoded in the radiation, even though you thought it was sitting inside the black hole, so it's not actually hidden from someone who has the radiation. It's the same thing here. I thought I was throwing Dari into a black hole and it was going to save me, but then just had to wait for a little bit more stuff to evaporate, and then by looking at all the radiation, including the early radiation, I'd be able to learn what the state of the black hole was. Right? That's the idea of entanglement wedge reconstruction. This region, the island, is the entanglement wedge. It's the stuff between the quantum extremal surface and
right, like the known locality of gravity sort of becomes activated when there's too much entanglement.
Yep, you have enough degrees of freedom that if you do something, admittedly something very complicated on this radiation, then you can sort of pull this Dari out of the black hole. You can pull it out by creating a wormhole, in fact, if you really go through the calculation in detail.
Also, this sort of looks like a phase transition in some sense. What does that look like from the CFT perspective?
It's a phase transition, it's a first order phase transition in the sense there's change of dominant saddle, but it's only a change of dominant saddle for certain calculations. So it's not like the CFT itself is changing phase or something. Well,
I'm not saying it's like a confinement to confinement thing.
It's a phase transition in as much as, it goes from the CFT being not thermal to being fully thermalized and just being in a maximum entropy thermal state. That's the phase transition, but I don't think that's a nice way to say it than
that. So when we were deriving the page curve before, it looked like dominant terms were the ones that came from the topological part of the action, right? And there's something that is highly two-dimensional that depends on the fact that we're studying just two-dimensional black situations. Do you have?
Yeah. So if you dimensionally reduce a higher dimensional thing, then that topological term ends up being determined by the transverse area. So it really is for the same reason that the dilaton is determined by the transverse area. So you could imagine taking high dimensions. So you get the same suppression. It's again by area. I mean, the easiest way to see this actually is just, the wormhole contribution is really just doing the QES prescription, right? The wormholes are that you prepare this state on this slice, and you prepare n copies, but then the boundary conditions end up meaning the dominant saddle glues this thing on one sheet to the same thing on the next sheet, and that glues together the different copies and creates a wormhole, right? But I gave you a completely general derivation yesterday that when we take the limit n goes to 1, then the sort of action of the QES prescription of that saddle is just given by the area of this thing plus bulk entanglement entropy. So that's the way to see it, is the area in that context too. But yeah, you could also take limits. You can see where the topological term comes from in dimensional reduction. It is the area of a transverse sphere.
Okay, thanks.
Okay, good. If there are no more questions, I think we can thank Geoff again. And so we start again at 11:30.